Dear experts, greetings. I'm Haojie from the School of Chemistry and Chemical Engineering at Shihezi University in China. I'm affiliated with the State K Laboratory incubation based for green processing of chemical engineering and serve as the leader of the innovation team for chemical process identification CPI. Today, I would like to present my research on the heat transfer and flow performance of a triple pipe millimeter channel reactor TPMCR. I will present my report from the following perspectives. First, let's look at research background and research ideas in the process of chemical production. Fast and strong exothermic reactions are commonly encountered. Traditional reactors, such as cylinder reactors, pose a potential risk of small runaway, which can easily result in combustion, explosions, and other hazardous accidents. Therefore, we should strengthen research and development of technology and equipment for the intrinsic safety of chemical hazardous processes, aiming to ensure that chemical production is inherently safe. Currently, macro chemical technology is a pivotal technology for achieving safe, efficient, and environmentally friendly chemical processes. Therefore, the utilization of macrochemical technology is proposed as a solution of these issues. The characteristic size of macrochemical technology typically ranges from tens to hundreds of microns due to its short diffusion distance, large specific surface area, and so on. It exhibits rapid mixing effects, excellent heat and mass transfer efficiency, high internal safety levels, and process controllability. Consequently, it finds extensive applications in various fields such as chemical engineering, food processing, energy production, and so on. However, macrochemical technology also has its limitations and key scientific and technical problems. There is a problem of insufficient single-channel processing capacity, so it is necessary to accurately build a high-flux macrochemical equipment, which involves issues such as amplification principle and scale effect. Currently, there are three scale-up methods to accurately structure high flux. Currently, the first is parallel amplification. It's numbing up that a large number of reaction channels are placed in parallel to achieve the processing capacity required for industry production. The second is similar amplification. In other words, a scale-up method which reasonably expands the characteristic size of the reaction channel. The third is the intrinsic amplification. In other words, the scale-up method which reasonably expands the character size of the reaction channel. The third is amplification. That is, by designing the reactor so that it has a large capacity of intrinsic amplification method. The content of this exhibition is mainly to propose solutions to the problem of scaling up the annular gap of a double pipe macrochannel reactor. At this point, in addition to considering the mass transfer reaction, mixing, and other related problems in the annular gap, the heat transfer capacity should be considered. Therefore, we propose a novel triple pipe millimeter channel reactor TPMCR, which can retain the advantages of microchemical technology increase single-channel processing capacity, solve a related blockage problem, and broaden a range of industry applications. However, when the heat transfer area per unit volume of TPMSR decreases, the energy density increases significantly. Therefore, we need to conduct the design and development of a TPMSR to mitigate heat accumulation during the reaction process, minimize potential safety hazards, enhance the intrinsic safety level of the chemical industry, and provide scientific and technological support for ensure secure and stable operations in chemical enterprise. Next, we explore the heat transfer performance of TPMCR. First, we built a TPMCR with different inner annular gap sizes, and the follow model of the three lines was counter-current influence of parameters such as the size of inner annular gap, inlet temperature of hot fluid, and the volume flow of fluid on the heat transfer and flow performance of TPMCR was studied through experiments. The heat transfer and flow performance of TPMCR were evaluated by examining the efficiency, friction factor, and Nusselt number of the annular hot fluid in TPMCR. The results of TPMCR were comprehensively compared with those of the double pipe millimeter channel reactor DPMCR. The specific comparison geometry was shown in the table. In the inner tube of inner annular gap sizes of DPMCR and TPMCR were consistent, which was convenient for comparison. Heat transfer efficiency is used to evaluate the heat transfer performance of equipment, which plays a crucial role in evaluating the application of equipment in actual industry. Therefore, the comparison of the efficiency of DPMCR and TPMCR is first looked at. Figure shows the change of the efficiency of DPMCR and TPMCR with the size of Reynolds number and the inner annular gap, as can be seen from the figure. Under all test conditions, the efficiency of TPMCR is higher than that of DPMCR. The efficiency values of DPMCR and TPMCR both decrease first and then increase with the increase of Reynolds numbers. The enhancement factor is the efficiency ratio of TPMCR and DPMCR. If the ratio is greater than 1, the strengthening effect will be better. This figure shows the enhancement factor radar diagram on the different hot water inlet temperature, inner annular gap spacing size, and hot water flow rate. It can be seen from the figure that the strengthening factors are all greater than 1, and the enhancement factor range from 1.45 to 1.65. This is the condition for achieving the maximum enhancement factors. It can be shown that TPMCR and DPMCR have higher efficiency advantages. The comparison of heat transfer rate per unit volume between DPMCR and TPMCR on different conditions was further analyzed. It can be seen from the figure that the heat transfer rate unit volume of DPMCR and TPMCR increases with the increase of hot water inlet temperature of all hot water volume flow. However, the heat transfer rate unit volume values of DPMCR and TPMCR decreased significantly with the increase of inner annular gap says the heat transfer rate unit volume of TP-MCR was higher than that of DP-MCR in all cases. Compared with DP-MCR, the heat transfer rate unit volume value of TP-MCR is improved by up to 65.4%. Firstly, the friction factors of DP-MCR and TP-MCR under different conditions are compared, as can be seen from this figure. Under the same inner annular clearance set, the friction factor of DP-MCR and TP-MCR are almost equal under all other experimental conditions, such as different hot water inlet in temperature and different Reynolds number. It can be seen that the friction factor is not the reason for the insignificant increase of TP-MCR unit volume heat transfer. In addition, the effects of different Reynolds number on the inner annular clearance sizes on the friction factor of TP-MCR at different hot water inlet temperatures were also discussed. As shown in this figure, it is found that the friction factor of TP-MCR decreases with the increase of Reynolds number in all experimental conditions, with the increase of the size of an inner annular gap, the friction factor values increasing. The comparison of the Nusselt number of DP-MCR and TP-MCR under different conditions shows that the Nusselt number of TP-MCR is lower than that of DP-MCR in all cases. Compared with TP-MCR, the maximum Nusselt number of DP-MCR increased by 50.7% and the minimum Nusselt number increased by 21.8%. The influence of DP-MCR and TP-MCR on heat transfer rate per unit pumping power under different conditions in further analysis. The heat transfer rate per unit pumping power of DP-MCR and TP-MCR increases with the increase of hot water inlet temperature. The volume flow of hot water decreases with the increase. It increases with the increase of the size of the inner annular gap. The results shows that the heat transfer rate per unit pumping power of TP-MCR is higher than that of DP-MCR when the inner annular gap size is 0.5 mm. However, as the size of the inner annular gap increase, we found that the heat transfer rate per unit pumping power of DP-MCR is higher than that of TP-MCR at a low flow rate. In addition, in order to provide a certain optimization and designs for the application of this new TP-MCR in industry, based on the experimental data, we established 3 different dimensions correlation formulas of Nusselt number, friction factor, and efficiency of TP-MCR. It is found that the maximum deviation of Nusselt number, friction factor, and efficiency between the predicted value and the experimental value is 8%, 4%, and 11%, which indicates that the feeding effect is good and can meet the requirements of engineering calculation. Here are the main conclusions we can conclude from the previous study in view of the essential safety problem, heat transfer of a strong exothermic reaction system. After macro-channel amplification, the TP-MCR has potential feasibility and application value. In this part, I would like to introduce our innovation team for chemical process intensification (CPI). Our team culture is scientific focus, pursuit of excellence, willing to contribute, one cooperation. Our team goals are faster process, smaller size, pure product, and all the efforts of our team aim at upgrading the levels of industry technologies and promoting transcendent developments of industry. The following is our team technology advantage 1. Molecular simulation methods for complex chemical processing. The following is our team technical advantage 2. Multi-phase process identification equipment development and scaling up. The following is our team technical advantage 3. High-share mixer reactor. Internationally, we are the team that has published the most papers in the field of high-share, and our team's technical support, Shanghai Fluke, ranks among the top 3 in the international field of high-share mixer. The following is our team technical advantage 4. Macro reactors, which are mainly used in fast and strong exothermic reaction systems. The following is our team technical advantage 5. New type of tubular tower reactors, which are mainly used in finite rate gas, liquid and liquid reaction systems. The following is our team technical advantage 6. Multi-objective optimization and system integration technology. The research focus is on developing in multi-objective optimization method for chemical processes and promoting green continuous process development. And finally, heartfelt thanks to the Ministry of Science and Technology of the People's Republic of China, the Ministry of Education of the People's Republic of China, the National Natural Science Foundation of China, Tianjin University CPI, Shihezi University CPI, Shihezi University, and Fluke Hybrid Technology Joint Research Center, Tianjin University, and Fluke Hybrid Technology Joint Research Center, and so on. Thanks to 5th floor Innovation Building, Shihezi University Building 50, Beiyang Campus, Tianjin University. Finally, thanks again to all the experts. Thanks for your attention.